Hi students, so in this last part of the video here, part 3 of the geometric series and sequences, we're going to talk about the sum of an infinite geometric series, and then we can look at some applications. So the sum of an infinite geometric series is where you have just a series that just continues on and on and on. It doesn't stop. And when you can find the sum, it says here when the common ratio, the absolute value of it, is less than 1. So this has to be decreasing. It can't be an increasing series here. So notice in this particular example, you have 1/2, and then if you multiply 1/2 by 1/2, you get 1/4. If you multiply that by 1/2, you get 1/8. And multiply that by 1/2, you get 1/16. And notice this is just getting smaller and smaller. As this gets multiplied over and over and over, this number is slowly approaching 0. So again, this is a decreasing geometric series. And r is going to equal 1/2. So if we were to find the sum of this, we need to know a sub 1, and a sub 1 again is the first term, so that is 1/2. And r is equal to 1/2 as well. Again, if you wanted to find r, just to make sure, you could divide 1/4 by 1/2. Remember, divide a term by its previous one, and then you'll get the common ratio. And you have to make sure that the absolute value of that is less than 1. This is already positive, so we don't have to worry about that. This is not an alternating sequence. But they might show us one in here that is. Or if it's the same sign, I should say. So for this one, again, to find the sum, the infinite sum here, we would be doing 1/2 on the top divided by 1 minus r, and r is 1/2. So this would be 1/2 divided by, and then 1 whole minus 1/2 is 1/2. You could get a common denominator for that if you needed to. 1/2 divided by 1/2 is 1. Anything divided by itself is 1. So this sum is 1 when you add it all up, this infinite sum. And it says here, for an infinite series, this index of summation I takes on the values 1, 2, 3, and so on without end. And again, to calculate the values for I, when they keep increasing without bound, we say that I takes the values from 1 to infinity. Okay, and again, r is less than 1, the absolute value of it. The next example that they give us is the sum of an infinite geometric series written with the sigma notation. And so you have I equal to 1, and this is showing just what I said before, that the index of summation goes on to infinity here. So here you've got the first number, a sub 1, and then it shows us here, this is the r, this is our common ratio, and then it shows us to the I minus 1. So again, this is an infinite geometric series with the first term equal to 8, and the common ratio, again, is 3/4, and it's less than 1. So we know we can find the sum for this one. So our sum is going to be a sub 1, remember. So it's going to be a sub 1, which is 8, divided by 1 minus the r value, the common ratio. This is 8 over, and then 1 whole minus 3/4 is equivalent to 1/4. And remember, 1 whole can be written as 4/4. So 4/4 minus 3/4, 1/4. And then keep, change, flip if you want to think of it like that. So 8, and then we'll multiply by the reciprocal. So we'll do 4/1, right? And then that's going to be 32. So this particular sum is 32. Two more examples. Okay, so the last two examples are going to be applications. Example 9 is follow the bouncing ball. So it says, suppose a ball always rebounds 2/3 of the height from which it falls, and the ball is dropped from a height of 6 feet. Find the total distance that the ball travels. So it starts off as 6. And then from there, if you want to find the next term, it says the ball always rebounds 2/3 of the height. So the next height when it rebounds will be a 4. 2/3 of 6 is 4. And then if you multiply this by 2/3, you get 8/3. Multiply that by 2/3, you get 16/9, and so on. And so what they want you to do is find the total distance that it travels. Okay? And again, they're talking about the vertical height here. So it says here, the ball falls 6 feet and rebounds. And again, the following series is the total distance the ball falls. So you're thinking of the ball falling. The distance that the ball rebounds is also given by, so think about falling, now rebounding. So if you think about this, I guess, it falls 6 feet, right? And then it rebounds, and then it falls again. So this is the one that's the 4. So notice it falls 6, falls 4, and then it falls again. That's going to be your 8/3, okay? But then we're talking about rebounding here. Rebounding is only counting the 4. So we're going to start here, 4 plus 8/3, and then it'll count these numbers here, 16/9, and so on. So we got falling and rebounding. And again, they wanted total distance. So we actually are going to be adding these up, which is really interesting. So each of these series is an infinite geometric series, and they both have a ratio of 2/3, okay? They just have different beginning terms. So let's look at the sum for the fall. I'll just call it sum of the fall. So this is 6 over, and then 1 minus 2/3. Okay, so this is for just the falling, the distance of the falling. So 6 over, 1 whole minus 2/3 is 1/3. And so this is 6 times 3, which is 18. So it travels a total of 18 when it is falling. And then the distance, the total distance it travels for the rebound, so that's going to be 4 divided by 1 minus 2/3. And again, 1 minus 2/3 is 1/3. So this is 4 divided by 1/3. And that is 4 times 3, which is 12. So, so now we have total distance traveled. Falling and rebounding would be 18 plus 12, which is 30. So altogether 30 feet.